Hello everyone, welcome to Lecture 10, which is the very last reinforcement learning lecture. Today we're going to be looking at extensions to a lot of the papers we've seen so far, which are really scaling them towards where the state of the art currently is. Now, up to this point, maybe you've had a few attempts at building and training an RL agent for the coursework, and my expectations are that the majority of you probably won't have done much self-study at this point, or really reading too many of the state of the art papers. And it may be that as a result you've not made much progress with the scores. And firstly, I'd like to really clearly state, don't worry, this is the game Gravatar we're talking about, and it's natural for many approaches to not work in this environment, which is one of the reasons why I set it, to give kind of realistic expectations of the true state of the field, rather than just overhyping it on some toy games. But even recent papers often only get a couple of 100 points for Gravatar, and very, very, very few of them are actually superhuman. So you're certainly not expected to reach that stage with this assignment. So before I begin this lecture, I'd like to really clearly state, don't panic, don't give up, just try your best and investigate and implement what you can, and you'll be marked fairly and accordingly. And the same applies for the deep learning assignment. Remember that the examples that I showed are indeed just exemplars for Sci-Fi 10, so if you can only generate a blurry mess, that doesn't mean you're going to completely fail outright, as long as you've tried your best and written up your experiments clearly. So I'm not really expecting a new state-of-the-art results for either of these assignments. I'm not expecting realistic Pegasus images, and I'm certainly not expecting human level performance in Gravatar. So I hope that kind of helps manage your expectations and eases any concerns. However, in this lecture here, I will be showing how to take the foundations that we've learned up to this point and really build on them to actually achieve the state of the art. And this is going to apply for complex games like Gravatar, and also will sort of work towards the very, very complex games, even like AlphaStar, where it's solving StarCraft 2. So it is possible to actually get scores of over 10,000 with the assignment, or even over 20,000, but you can still get first scores with very low hundreds if you had a really good go at it and you've taken the content on board. In other words, I definitely won't be applying just some linear function to people's scores and grading based on that. So I kind of appreciate this can be scary if you haven't got like an amazing agent and you might feel like you're going to fail. But with that being said, we will be working our way towards the state of the art. And as you see today, this mainly does involve integrating more advanced aspects from the deep learning course, such as recurrent architectures, to anticipate better long-term rewards and using a few tricks to improve the agent exploration. Alright, so if we just have a bit of a recap of DQN, or DQ networks. If you remember, we have some agent in an environment, and that agent takes an action, such as moving the Atari joystick, up, down, left, right, or pressing the fire button. Then the environment, it spits back the next state, which if you like is like the next frame of the game, and you get some reward signal, like your score increasing. And within DQ networks, or DQNs, if you remember, these were like temporal difference methods that learnt to estimate the action value function, and it did that by updating the initial estimate a little bit in the direction of the TD error, which was the reward plus the discounted value of the next state. And this is all a valid derivation of the Bellman equation, combining the optimal policy while also following some exploratory behavior. And we showed later that we can use function approximators for this with various tricks to make them non-IID and more suitable for training. We saw how this can actually work quite well. Alright, so what's actually the problem with doing this? Well, in theory it's nice. Consider like this Atari Sequest game over here. You play as this submarine. You have like an unlimited supply of missiles, so you can pew 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 and shoot down the sharks, and you have to kind of rescue the divers and shoot down the sharks at the same time, and then resurface to let the divers get off your submarine. So it's actually quite trivial to estimate the reward. If you shoot down one of the sharks, one of these green things, you immediately get more score, and so you can estimate the value function very easily. You get more value the more sharks you kill. You directly get points awarded for shooting an enemy. You're always losing oxygen as well, so it becomes clear that you need to move quickly, and you get lots of points when you rescue the divers, so it becomes clear that this is like a good thing to do. And this also works really well in games like Pac-Man, where you've got that yellow character that eats those little dots in a maze, and every time you eat one of the dots you get some score. Whereas if you get hit by the ghosts which move around, you lose a life, and then eventually the game ends. So estimating the value function in those kinds of games is really quite trivial, as the advantage can be quite easily estimated. So in Sequest here, Atari Sequest, we make sure we're always shooting at the shark. So there's no reason not to just keep firing. And in Pac-Man, we're always going to want to be exploring and finding the places with the most dots and eating them. But now let's look at more challenging cases. There's actually an Atari game called Montezuma's Revenge, and also you know Gravatar at this point because it's in the coursework. But Montezuma's Revenge is, you can Google it if you like. It's like a 2D platformer, a bit like Mario, but it's not quite so linear. You only get reward when you complete a level, so you've got these screens or these scenes, and you have to complete them. And to complete these levels, you need to climb various ladders, you need to solve puzzles, go back on yourselves, collect keys, go backwards, forwards into different, almost like a maze-like environment, which is always changing. You need to avoid the enemies and so on. And only after you've completed this very, very complicated sequence of actions, things which are actually quite intuitive for humans, like putting keys in locks of the same color, then after all this long sequence of actions, you actually get some reward. And similar with the game Gravatar, you often get thrown into different planets where sometimes the enemies are nested very, very deeply within various obstacles or tight spaces in a level, like having to navigate through this entire spiral. And you've got to not only do that, but you've got to fight against these complex gravity controls, so you've got very difficult controls. And sometimes, you've got these mazes where you've got to navigate in this completely different environment to get any reward. Alright, so back to the diagram. In Atari, you've kind of feed every action into your neural network, and then you get some prediction of the Q value. And wherever the Q value prediction is at the highest, that's the corresponding action you would pick. And the Q value is basically the reward that you're expecting until the end of the episode. And this tends to work really quite well for twitchy games like Pinball or this Sequest game over here, but not for games where the reward credit rolls and propagates far and far into the future. Like here, you've got to go through all of this to get some reward at the end. Okay, so that's the kind of problem with DQN as we see. It's this fact we've got to somehow explore further into the future, and it's just not very well designed or suited for that. Now, a significant improvement on this is the R2D2 agent, which stands for Recurrent Replay Distributed DQNs. This was accepted at ICLR last year. You're going to see a bit of a theme of this. A lot of the papers that are really pushing this state-of-the-art are from ICLR. So R2D2 uses a recurrent neural network architecture that trains on a long history of observations. So unlike in DQN, it doesn't just receive one observation of a state and an action as input to the neural network. Instead, the neural network receives a replay sequence of observations at various time steps, alongside the actions you took at those time steps as input. So it takes a sequence of about m equals 80 inputs, and these all get fed into a recurrent neural network. So that kind of integrates all of this into the current representation, the current state representation. So the agent doesn't just see what's happening right now, but it's got all of that information of what happened previously to decide on, and it can actually backpropagate through all of those things to learn the long-range reward assignment. So it can figure out which of the earlier actions had the most influence on the current reward, and so it's quite effective and efficient at doing this. The other important part of R2D2 is that it's more distributed, so it can squeeze a lot more juice out of parallel hardware. So in distributed RL, you have a centralized learner instance, or this blue network here, and it has some weight parameters, say theta. And then the learner receives multiple streams of experience. So this is from your replay buffer, but they're you get lots of them coming in at once. And then these streams of experience here are actually gathered up from numerous parallel workers. So you can imagine lots and lots of parallel threads if you've got parallel hardware, or even on multiple GPUs, you can have these parallel workers, these red actors, if you like. And each one of these red workers, they run the episodes independently that does the actual interacting with the environment. So they collect all of these experiences, and then they send their experiences back to the learner, who then updates their weights accordingly. And this is, I don't know, if you want a metaphor, this is a bit like how R&D or research and development gets done in the very big corporations like Google DeepMind, where you have some central celebrity-like professors, so someone like David Silver or the CTO in blue, and these have like, these people are very clever and they have the initial ideas, and then you've got like this big team of people under them, this big team of software engineers, and these are the actors or the programmers, the sort of research assistants in red here. And these people do the actual simulations. They run the experiments, they're the scientists, they interact with the environment, and then they sort of create reports and report back their experimental findings. So you can imagine like they're all writing up the reports of their experimental results, and they're filing those away into this experience replay buffer here, this green thing. And then these get sent back to the CTO or to the big chief, the person in charge, and this person then updates their strategy, updates their hypothesis, forms like a new research plan with the team, maybe publishing some papers and farming citations and so on. But it is actually a very effective, fast strategy for doing research, and it's also a very effective strategy for reinforcement learning, because it allows you to sort of offset the load and distribute the load to lots of workers, which can all maximize the occupancy of the parallel hardware, report their experiences back into this buffer, which can be read back by the learner. So how well does this perform? Well, now that you're familiar with Gravatar, I pulled these specific charts out from the paper. But for Gravatar, training with this approach can easily beat my last score, which was around 7,250. And actually it can score, if you see the extensions of this, it can actually score over 20,000 points. So let's just have a video, have a look at these two videos which show the R2-D2 agent in play. So this is R2-D2 playing Gravatar. Again, it's not really playing like a human. You can see it sort of circling. And you might think, well, it just killed itself. Surely it's not that good. And later you'll see that was actually a very good strategy. So it's really quickly going through this level, even killing itself just to exit faster. Why is it so cared about? Why is it really concerned about if you really think about it, it's conserving its fuel a lot. It's not using much fuel at the moment. So it's really, really fast going through these levels. It's got a very strange policy to do it. Now it's exiting this world as quickly as it can. It's just sort of going through these planets as fast as it can. Boom, boom. Out we go. It's very, very quickly. So it's already got 12,000. It's already beat my score. I would have taken already sort of 5 minutes to get anywhere near this. And then here's where it starts to get interesting. It starts to farm this enemy up here who reappears and respawns. And actually, look at the small amount of fuel consumption it's using now. So it's kind of managed to exploit this part of the game where it can just keep farming this energy using very, very little fuel. And actually, for the rest of the video, it just stays in this one position, gradually losing fuel and gradually increasing its score. So it's basically stuck in this local minima, but it does get a very, very good score at the end because it knows it can just stay here and exploit it. So this is really worth reflecting on. This is a really good example of a problem actually with this R2-D2 approach. It's very effective, and it's clearly learned a very good strategy. And it's quite surprising, like how many humans would think to just stay here and farm that little part there, and it gets a score of over 20,000. This specific R2-D2 agent, and then eventually it runs out of fuel and the game ends. Okay, so there's a kind of problem with that. It does get stuck in this local minima, and it does. Why would it want to leave it? Because it's good to just keep exploiting this over time. It doesn't really continue exploring. So the real question is like how can we get out of this local minima? And just for fun, this is the same agent on Sequest, where it just very, very quickly sort of hunts through the enemies, picks up the divers, and so on. You might want to watch that yourself, but there's another link for those kinds of fun videos. But yeah, returning to this, how can we get out of this local minima? How can we do more exploration? So let's just sort of zoom out and pause a bit and talk about this exploration and an exploitation problem. And just sort of reflect on what we've been doing up to this point and the kind of approaches we're doing. So I guess the problem with R2D2 is that it's not very good at balancing exploration with exploitation. So up to this point, we've only really discussed stochastic approaches that, with some probability, like the roll of a dice, they just pick their actions randomly. So we've looked at these epsilon greedy strategies that, like I said, roll a dice and then they just pick a random action, otherwise they exploit the environment with some probability. And we looked at approaches like greedy at the limit of infinite exploration, where you sort of anneal the randomness down, so it ends up exploiting, but it starts off, but at the limit it explores everything and exploits everything. Alternatively, we have this softmax approach where we learn a distribution over our actions and sample from this. We learn some distribution. We take our action space, put a softmax over it, and then we can sample from a probability distribution. So it's again stochastically choosing a random action, but according to some probability or with some important sampling. So the question is, can we do better than this? Well, we can consider some more semantic functions for exploration that model more natural or intuitive ways to explore an environment, maybe more like how a human might explore an environment. And the first approach is called optimism in the face of uncertainty. And this basically says, if you're uncertain about the value of something, then you should prefer to try that action. So if you're uncertain about part of the environment, then you should try and explore it. So in the middle screen here, or Gravatar, if you've one action which is to just return to the previous screen, where you can shoot the ship and get a reward of 10, or another action which is to try and go down a bit and explore a bit more of the map, then the idea here is that you should actually favor the action which you're less certain about. So if in your episodes you often just go back and shoot that ship over again, or if you keep farming that part of the local minima, the idea is that that's going to become very predictable, very boring, and you're very sure about what you're going to get. So it's actually, you negatively weight that. So you prefer to do new things. So it's not like randomly doing new things, it's just saying we give preference to things that we're not sure about. So this would basically mean that we don't know what's over here, or we've never been over here before, so we're going to prefer to go over here. And if you crash into this wall over here, that's quite predictable. We know that if we're in a state and there's a wall and we hit the wall, then we know we're going to die and reset, and that's actually quite predictable, that what happens when you die. So it's not actually going to want to just keep crashing into the walls. It's going to really want to go through and navigate and find whatever that thing is in the middle. So this kind of optimism in the face of uncertainty strategy, it favors taking risks with potential for high reward. And in the long run, this means that we could be more confident in getting the most out of our environment. And in this case, we're going to explore the spiral and get the most long-term reward, hopefully. And actually, from my old group of friends, just out of incidentally, the very wealthiest ones I know now are the risk takers, the ones who invested a lot of their own money into startups at the beginning, took massive risks that I definitely wouldn't be doing myself with a family. So while it's not necessarily always the best strategy for real life, it does actually quite go against our human nature. But actually this can work really well for model-based reinforcement learning, where you can imagine the outcomes of taking the risks in certain situations. So it's like you can close your eyes and imagine what's going to happen, and that can be where we do our risk-taking. And then once you've discovered that this new part of the environment, say over here, you can then take it again and again and again. And that's like in this Age of Empires example over here. It'd be a very bad strategy in this game to just collect the visible resources, these trees and this ore, on the map, and that it'd be very bad to just keep exploiting those, and you get it quite predictable, and it would also be bad to just randomly move your units around the map, with this epsilon greedy approach, just randomly taking actions. That would be a very bad strategy. What would be much better to do is to have your units explore the areas that you've never seen before. So just to send out scouts around the map. So you select some of your villagers, or this one on the horse. A good strategy would be to send it around the map first, because it's not certain about the value of those parts of the map. And then in this process, it might discover like a high value resource, like a rare gold mine. And once this is discovered, you can then just keep going back and exploiting that gold mine until it catches up that it's predictable and you want to do more exploration. And similarly, if that bit of the map has nothing there, so if you send your horse out and there's nothing there, you can always just go back to exploring new parts of the map again and exploiting the resources that you already know about, coming back to this resource over here. So to quantify this kind of uncertainty, we can generally use frequentist or Bayesian methods, and we'll look at a few examples in a bit. But lastly, the most computationally expensive approach is to consider the information state space. And this means we consider the agent's information itself as part of the state space. So one state may be that you're in like a corridor and you don't know what's inside any of the doors. Maybe there's some doors along the corridor. And another different state might be that you're in the same corridor, but you now actually do know what's behind all of the doors in it. And then you say, that's actually a very different state. So the idea is if we expand our state data to include the information we've acquired for each given state, then we can actually quantify how valuable it is to find a new piece of knowledge. And so we can say how valuable it was to discover this rare gold mine or whatever it was. And we can understand and quantify how valuable it is to accumulate new information. And while it's great to be able to quantify this, it causes the state space to explode in size as you've got to store all of this additional information in the state space. And often that's actually considered too computationally expensive. But it's interesting to know just like that's a clean way to do this, but it's very expensive. All right, so Never Give Up is yet another recent ICLR paper, and this builds upon R2D2 as we've just seen, and it continues to improve on the results of it. The central idea, I suppose, is that in addition to the reward that you get from the environment, we actually introduce another reward term here, and we call this the intrinsic reward. And basically, the agent gives itself its own reward, so we're showing this reward here in purple. So it's like we get this environment reward from the environment, but the agent also is able to, according to some heuristic, reward itself, and we actually just add those two things together. So more formally, we say that the reward that we consider for the agent is both the sum of the environment reward, this environment reward at this time step, and the agent's own internally decided intrinsic reward that it gives itself. And this is designed to encourage certain behaviors such as, in particular, curiosity, novelty, and exploring around. So this additional intrinsic reward that the agent gives itself can actually be weighted by some scalar, beta, so we can choose how much the agent values the environment reward in comparison to the exploration or the novel behavior that it rewards itself with. So it's like you're preconditioning the agent and telling it it's good to be creative, it's good to be novel. I tell my kids, it's a really good thing to create things, and I reward them, and hopefully they build this idea up that it's good to be creative and try things out. So it's like they reward themselves when they're creative. So going back to our Age of Empires example back here, the agent can learn that it's a good thing to uncover new parts of the map. It rewards itself when it starts to find things that it's not seen before. Because it's surprised to discover things it's not seen before. So it rewards itself. And similarly in the game of Gravatar, this means like the agent really wants to explore through that whole spiral. It knows it shouldn't crash into the walls. This is very predictable. It will die and reset to the beginning of the level. So it's kind of like this idea of novelty or curiosity. It's just very powerful. But it's still quite difficult to tune or adjust this beta value here to find the right exploration and exploitation amount. And this actually varies a lot per game or per scenario. And maybe you kind of need to tune it differently or dynamically, or you maybe even want to tune it for each different game. So for example, in Age of Empires, you might actually want to change how you have this parameter throughout the game. In Age of Empires, once you've discovered a really valuable resource elsewhere in the map, the optimal strategy might then be to just completely exploit that resource as fast as you can, get as much juice as you can out of it, and then you can build up your base really, really quickly because you've suddenly got this high value resource. And at that point, you might want to just put all hands on deck to farming that resource rather than to just keep exploring about. So you basically want to, at the very start of the game, have a very large beta value, which does a lot of exploration. And then you might find something very, very valuable and you want to just reduce beta to 0 basically and just exploit everything out of it. And then once you've farmed that, you might want to increase it again once you've, that rare gold mining resource has all been mined. So there's a few papers which do kind of do this thing. So one example, or one famous example, is Agent 57 by Google DeepMind. They kind of attempt to tackle this. I'm not going to show a whole slide on it, but their approach is basically the same as NGU, but for Q learning. And instead of learning one Q function, they basically split the Q function into two parts for the environment reward and for the intrinsic reward. So it's very similar to this equation here. And then they also allow weighting the intrinsic rewards by beta in the same way here. But the thing they do differently is they actually learn to optimize this beta value, and they also learn to optimize the gamma, the discount value, during play itself. And this is basically done with some outer loop meta-learning approach, which is basically like using reinforcement learning again to learn these two parameters. So it's like we use reinforcement learning to learn these things that we use reinforcement learning for. So it's really quite over-engineered. It's Google after all. And although the results are a little better than R2D2 in NGU, they're not hugely better. So there's a chance that it could just be overfitting to the Atari benchmark, which is why I'm not sort of adding a slide on it. But what was really good about Agent 57 is that it does beat the average human performance across the Atari benchmark suite. So that's quite an important sort of roadmark or landmark in the field. Okay, now we're going to look at another recent ICLR paper, and this one's called Dream to Control, Learning Behaviors by Latent Imagination. And this paper is shown to work really well in continuous action spaces, and you can see, as you can see from their example here, they have this spider-like robot, and the goal is to learn a movement policy for this spider, and they want to make it move as fast as possible. This is actually a really difficult thing to do, to manually, if you're a robotics engineer, you've got to do all the inverse kinematics and moving all of the different joints which depend on all the other joints. There's a huge amount of maths, and it's very, very, very difficult to optimize that to get the final goal of moving this spider as quickly as possible. So the goal of this is to use reinforcement learning to learn this policy to move it. There's actually a recent extension to this submitted again to ICLR called Mastering Atari with Discrete World Models, which has this Dreamer version 2 agent. I'm not yet convinced this is better than R2D2 and NGU, but it's still worth unpacking and examining what's behind these papers and what makes them work. But the goal of this paper is, again, like before, to map from environment observations, these O's at the bottom here, observation 1, observation 2, observation 3, observation 4, to basically actions, or this A1, A2, and so on. So these actions are basically what say how much and how we should move the robot's legs and in what way we should move them. Then after you take an action, you advance to another state, and then you get another observation out of it basically, and then you get your reward 2, which is basically how far you've moved. The goal is to move this thing as quickly as possible. And the way they do this is by kind of dreaming or imagining using the latent space, which, as you know from deep learning, if you sort of remember an autoencoder and remember the latent vector in the middle, it represents a compressed abstract feature representation of the state. So in theory, it's easier to imagine things in terms of this high-dimensional, deep and abstract concepts. And then if we could actually learn these features representations, these deep and abstract concepts, we could actually do our planning just based on those. So I guess let's give a metaphor for this. It's a bit like when we turn the lights off and we close our eyes, we can kind of plan what we'll do tomorrow using these deep and abstract latent feature concepts. Like you can imagine just kind of close your eyes and thinking, what am I doing tomorrow? I'll go to the shops, maybe I'll drive my car, get an MOT, I'll do this kind of stuff, and then what am I going to do from that? Is that going to be the best way to take my day? Maybe I need to send an email. Oh, if I forget to send that email, that'll be really bad. So you're doing all of that planning without actually experiencing it, and you're doing it all with these very, very deep words and concepts in your mind. And this is basically what's happening here. We're trying to plan ahead using just these deep, learned, relevant concepts and features. So the question is, how do we get these latent representations, these green parts here? How do we learn good representations? and you just feed an input state or your observation through an encoder. Or maybe your inputs or the observation as the game's ran, you throw that through some encoding function. So if you had like pixels, this is basically just like having some convolutional autoencoder which decreases the spatial dimensions, just like you were building a classifier. And this part here is just like the bottleneck layer for that classifier, if you like. And from that hidden representation, you can easily map it, just like again in a classifier, to the next action. So this is basically just like categorical cross entropy, trying to classify the actions effectively. And then you get like a new observation, you encode it. It gives you this green hidden space, this latent vector, like the middle part of an autoencoder. Then from that you classify the actions. The difference is that you can combine this green part here with you can also condition it on the previous input, the previous hidden state. And actually this part here, you'll then see, because you've got this additional conditional of the previous state, this is actually just a recurrent neural network. So the green part's a recurrent neural network, and then the blue part here is basically just like the encoder from an autoencoder. Later we'll see this as the decoder. So you can code this in any way you like using, say, an LSTM or a GRU, and in Dreamer v2 they use a GRU. So actually, I should mention, to actually code the architecture for these recurrent neural networks in PyTorch is really, really easy. You don't really need to code it yourself. You can just use like nn.gru cell, which is like one of these cells within this recurrent neural network, and there's loads of parameters you can do for it. So it's just a question of choosing the right defaults and setting the parameters. You don't actually need to code it, and using it correctly, of course. Okay, so what's clever about this? Why is this a good thing? Well, if we look at the middle diagram here, this learn behavior in imagination, you'll see that the model can actually do this whole thing just by imagination. So it can predict, using the GRU, the next hidden states without actually seeing more observations. You don't need O2, O3 to actually predict the next hidden states. And that's really, really cool. Basically, the RNN given the previous hidden state, so given this hidden state here, and after you've taken one of these actions, like A1, it will actually learn the next hidden state, or estimate the next hidden state, which corresponds to this kind of observation over here. And then given this hidden state and taking this action, it can learn the next hidden state, which corresponds to moving even a bit more further, updating the legs again. And that's really, really efficient if you think about it. If you think about how compressed these hidden representations are, this is already really directly mapped to the problem. So we only need to learn to do this important part here just from the relevant data. And this last figure on the right here basically just shows the final goal, which is to act in the environment, and you can do this when you've learned how to plan ahead efficiently. So how does this work? Well, the important part of this is to ensure that your hidden feature representations, these green parts here, that they accurately represent the current observation's state. So we want these green parts to capture all of the essential information within the observations. And then the question is, well, how do we learn a good representation for this green part? And then if we look in the lower left here, basically you have this, this is actually an autoencoder. It's normally like a bow tie shape. We've kind of just wrapped it back down this way instead. And this should be giving you an idea of how it works then. So to learn this green representation, we basically learn to approximate an inverse. So it basically learns to predict the original data. So we know that this representation captures all of the essential information by reconstructing the input observation. And then the GRU here, this part here, it predicts the transition as well. So it goes from it predicts the transition from one, state representation, hidden representation, to the next green hidden representation, and it also predicts the reward. So if we put all of that together and assemble everything, we now have all of our components for a reinforcement learning algorithm, but it's kind of elegantly decoupled the state from the high dimensional representations, so we can learn very, very efficiently just on those features that are meaningful to the actual reinforcement learning problem. Okay, so let's like look a bit deeper at this and have a look at the algorithm to make it more concrete. So just glancing at this algorithm here, you'll see it split into 3 parts, as with the 1, 2, and 3, as with the last figure. So we've got this dynamics part, this behavior part, this environment part. And then this first part here optimizes these theta parameters, which basically learn the representation, it learns the transition, and it learns the reward model. And that sets us up for the reinforcement learning part here. And this is the really cool part. The second part here, they call it behavior learning, or you might want to think of it as the imagination part. And this basically optimizes the parameters to determine the action and the value function. And then there's this third part here, and this is quite simple. This just interacts with the environment, where it basically adds a sequential trajectory of new experiences, basically into your dataset buffer. So it adds new experiences to your dataset. So let's just zoom in a little bit more closely at these 3 parts so we can kind of understand them a bit. So we'll start with the dynamics learning part at the top here, and we just see that we initially sample a sequence of experiences. We've got this sequence here up to this point from t equals k up to here. And we sample that from our dataset buffer D, and then we sample the model's estimate of the next hidden state. So we're basically saying ST conditional on the previous state, action, and the current observation. So if we go back to this diagram here, we're basically saying we can estimate this. Let's just say this is the next state, this is the current state, this is the next state. We want to estimate this next hidden state here, conditional on this O2, this observation, the previous hidden state, and the action we've taken. So to train this state, we need this arrow, and this arrow as well, all coming into it. These are the conditionals, these arrows inputs, and we're predicting the next state. ST given all of those informations. Okay. Then basically we update the parameters theta of this network such that the prediction of this next state, the green center, matches the actual next state. So this is from that. This is this decoder part here. We make sure that it maps well to the actual representation learned through this identity. And this can be compared basically to the ground truth. And then we have this behavior learning stage here. Now, in this part, this is a really cool part, I think. What we do is we imagine future trajectories. So this is from T up all the way up to here. We imagine these trajectories from the green hidden states. So we use the model that we've just trained to predict the expected rewards and the values from those hidden states. And then we update the model parameters to maximize the action and the value function. So we find, again, this is like the traditional reinforcement learning we've done up to this point. We find the action that gives the most long-term value, and this is done using regular reinforcement learning. But the difference is here that we don't update this using new observations. We do it all just using our dynamics model, which predicts the things that we need just from the green hidden states. So it's much more efficient, and it's way better at looking far into the future efficiently. So just flicking back to like the previous slide here, this is looking at the middle part here, and we can basically solve the reinforcement learning problem with this just by sampling this very, very efficient recurrent neural network without having to experience loads and loads of stuff or push it through the encoder. We can just operate directly with these tiny little relevant features which can capture all the essential information we need for the reinforcement learning problem. So it's much more data efficient, and it can look far ahead into the future very, very quickly. And it really is like when you close your eyes and imagine your current state and action, and imagine where your state and action will take you. If I did this and took this action, where am I going to end up? So, you can, again, with a metaphor, you can close your eyes and be like, if I read more reinforcement learning papers tomorrow, and if I study the author's code, and if I try and re-implement it, does this mean I'll get a better grade, or will I just get a better result if I keep modifying the current DQN code? So it's really like a thought process that it's modeling here. And because this RNN is just predicting the relevant deep and abstract features that map to your long-term value, where your predictors are only based on the other deep and abstract features, so it really is like, I don't know, it really does feel like it's how we as humans do research. We think in terms of concepts and words, and it really is modeling that behavior. Now, I appreciate this is all quite advanced stuff, but it is really very cool, and it can be trained efficiently on even a single GPU once it's implemented. But it it does take a very fair amount of architectural engineering to achieve this decoupling. So going back just quickly to the last part, this is really simple. This is basically just updating our experience buffer using trajectories of experience. So we sample from the history here a full trajectory of experience from t equals 1 to t, and then we just append this into our data set. And also we have this bit of randomness to not get stuck in some local minima. That's just basically doing the actual interaction. All right, so moving on, we're now going to sort of finish off with a more complete, or perhaps the most exciting current example of reinforcement learning, which is how it's solving StarCraft 2 with AlphaStar. So just a bit of context, StarCraft is a game with 3 factions. You've got humans, which are called the Terran, and then there's an alien race called Protoss, and these aliens have much more advanced technology and available to them. But there's also like this bug race called the Zerg, and these are very different to the Terran and the Protoss, and they're like this swarm of bugs which infect stuff. But the really cool part about StarCraft is the races, the factions, they're all very, very different. They have very different moves available to them, but they're actually extremely well balanced to the extent that professional players in any one of the factions, has an equal chance of winning. But what we want to do is we want to train an agent to play competitively against like some of the world's best players. And why is this really hard for reinforcement learning? Well, for a start, the action space you can take in this game here, you've got a mouse cursor, you've got tons and tons of units, each with unique abilities and things available to them. So you've got this massive, massive action space. And there's loads of ways you can manipulate your units. You've also got like a mini-map down here. You can take actions to actually move the camera around. So again, it's just very, very complex space to be searching in. And also the games are quite long. They can be 10 minutes long. So it's very hard to learn what actions you took early on contributed to the long-term value that decides just at the end you either win or you lose. So I'm not going to really have time to go into all of this in great detail. Basically, DeepMind, as Yannick Kilcher likes to say, they use every trick in the book to achieve the amazing results that they achieve. But I will just kind of break it down a bit so we can get some insight as to what's making this so successful. So I'll focus on how they solve it. But the first thing to say, if you read the paper, it's a Nature paper, is that they have many, many components where basically it feels like they've got a big team of sort of machine learning engineers to build lots of individual components to solve the different tasks. So it's like they have a network to schedule actions, schedule whether you move your mouse, need to move the camera or so on. And then they have another network so that you schedule these actions, or they call it delay. And then you have another network to prioritize these actions. So they're in like some queue and you need to work out which are the most important actions to take. Then they have another neural network to select the units that they should do the actions on. Another neural network to decide who should be targeted, whether you should be targeting other players or the enemies or so on. So it's got lots and lots of components, lots of neural networks addressing sub-problems effectively. And looking at the diagram on the left here, basically they train all of this with just standard, and initially with just supervised learning. So actually the beginning part's really easy to understand. They have lots of training data, which is professional human players playing, and they basically learn to classify or predict the way the humans are playing. So they're just literally training it like a teacher with standard supervised learning. So the first part's like, there's not really that much contribution to it. It's really just quite complex supervised learning, not really like, there's nothing particularly exciting here. It's just very, very over-engineered to solve the complexity of the game itself. So how well does this do is the real question. Like, just from supervised learning, this is where they get to. So this is AlphaStar supervised. You can imagine a horizontal axis, and this is like down here, sort of like the world's best players, grandmasters, and you've got like expert players and beginner players sort of over here. So it gets to like 85% simply by imitating humans with just simple supervised learning. So that's, it's already doing really, really well. But it has kind of been over-engineered and boring. But this is actually where things start to get really interesting, which is why I've got 2 slides dedicated to this. So if we look at things like AlphaGo, which uses self-supervised learning, AlphaGo, and AlphaZero, they play games against itself until they get better and better and better. This is actually called self-play, and it's a really exciting area of reinforcement learning. Just the idea of having, when you know the rules of the game, you've got a complete model, you can just keep playing against themselves and they progressively improve. But actually there's a few instabilities with this. It's it's very like a GAN, I suppose, in that you can get this rotation as you play against yourself. You kind of get stuck in this rotation through the modes of the distribution. So there's these instabilities. So what does DeepMind do to address this? Well, this is where I think the contribution is. They introduced this kind of league table where the agents don't just play against themselves, but they also play against old versions of themselves. And in particular, they prioritize how good the old version is. So maybe it's been playing against itself for ages, and it plays against all the old versions of itself. And maybe one of those old versions did particularly well, so it explored a part of the distribution, and it sort of learned some good strategies. So it sort of keeps that in the cache, and then it plays against that well-performing agent, or the one with the particularly clever exploits, and it plays against them more frequently. So if there's a high-performing agent in the past, it plays against that version more often. So this ends up creating this almost prioritized population of agents, a virtual league. So it creates a big population of agents that played before, and it creates this separation, this league. And another really neat thing they do is they introduce specialized agents into the league, and these are called exploiters. And these exploiters only need to play against the main agent, sort of the cherry of the population. They target these specific key players or these main players, but the main players have to play against both the exploiters and the past versions of themselves. So the main players are kind of disadvantaged. But then when the main player gets better, the exploiter gets sort of reinitialized, so it has to find new weaknesses in the main players. And it's basically like having a virtual personalized trainer who's looking out for your weaknesses, trying to exploit them, and then that trainer gets reset, so you get a different trainer when they've done their job. And it's really an effective strategy. If you look at their various ablation studies, you'll see this really does contribute to some important and insightful improvements. All right, so trying to look forward back and maybe reflect on what we've seen in today's lecture. Where are we heading? This is like a reflective view, my own view. So I kind of feel like a lot of these reinforcement learning advances are a bit overly complicated. I do feel like RL is missing a very kind of simple, novel, clean idea that beats at the heart of it. And this is actually a view shared by a few DL and RL researchers if you watch various interviews. So a lot of the important insights from state-of-the-art things like playing StarCraft 2, there's just a huge amount of engineering in this. It'll be much nicer if we can find a simpler, cleaner solution to these kinds of problems. And there are some papers which almost ran out of the box. AlphaGo was a really nice example where lots of different researchers, AlphaZero applied it into various other domains and models, and it did start to captivate. But it almost feels like we're deviating away from that towards more supervised learning and task-specific problems. So it'd be nice, and it maybe feels like in the future there will be, again, a comeback to simpler and smaller models. I think also there's a bit of a mismatch between the more advanced side of the generative modeling literature and RL. Maybe these need to come together more, and this is also a view shared by a few researchers. I do, however, really feel like this idea of self-play and these models of this league play idea is very, very important, especially as we think of like AGI as not just maybe a single model, but there's the potential that it could also be like a diverse distribution of programs all evolving together. So whether or not that's going to happen, or whether we'll end up unifying towards just a grand, centralized, single, massive deep learning generative model for maybe the whole planet at one point in the future, because maybe that's the most efficient way to do it in terms of the energy costs. Whether that's going to be the answer, to be honest, I'm not really sure yet. but maybe this answer will become more clear within just a few years. Okay, well, that concludes everything I've really wanted to say in this lecture series. Just a few general tips to finish off on. A lot of what we've done so far is just learning foundation concepts. In fact, the majority of these lectures have been, up until really this point, just learning the foundations of the field. And this is really so that you can speak the lingo now, such that you can read the papers and pick up what the key concepts are, because a lot of them do draw on the traditional models and experience and replace various components with function approximators. Having said that, this is really key, you may want to actually approach it from now on, now that you can speak the lingo, more like an engineer. So now that you can speak the lingo, I kind of recommend doing another strategy, which is a kind of top-down strategy. So this is kind of borrowed from a quote of Elon Musk. You know, if you've got an engine and you want to understand the engine, one of the best ways to do it is an engine is a very complex thing, just like a paper can be, one of these papers can be very, very complex. The best way to learn it is to kind of dismantle it back down. So run the code, try to run it maybe even without understanding it, and then break down the concepts and work out what makes this engine work, what makes this massively complicated algorithm work. And that can be actually a very good strategy for learning to read some of these advanced papers and just to get a feel for it. So it might be a good strategy to do in the coursework as well, is just to approach these complex papers like an engineer, implement some of the state-of-the-art things or as close to them as you can, and then try to understand dismantling it from a sort of top-down approach. Another reflective point is that sample efficiency remains a big issue in reinforcement learning. Even with these amazing ideas where you've got these very efficient, recurrent, imaginative models, still that you're trading at the end of the day the kind of amount of environment sampling you need with the imagination, and there's always this kind of trade-off: how much simulation do you do versus how much environment sampling, and this remains a kind of open problem and an open issue. And lastly, reinforcement learning can have very, very high variance, so trying to lower your variance is always a very effective strategy, and this will allow you to iterate faster without training for so long if you've got lower variance. All right, well, that concludes this RL lecture and the RL lecture series in general. As with deep learning, this has been great to teach this very interesting and exciting area. And I think I've said everything I really want to say now. Of course, a big thanks for this, and a lot of credit of it goes to Sutton and Barso, who really are the pioneers of this field. And of course to David Silver, who, like Elon Musk to the space industry, is one of the main people pushing the boundaries of what we think is possible in RL. He's the lead researcher of AlphaGo, AlphaZero, and AlphaStar, and I recommend watching his interview with Lex Friedman if you want a nice way to kind of wind down from this over Christmas. All right, well, that is everything I've wanted to say. I hope you stay safe and have an enjoyable break, and do keep in touch if you've got any concerns or questions.